Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. Hey, welcome back. This is part 9 of the mini course Preparing for Organic Chemistry. We're continuing our discussion of acids and bases in organic chemistry. There's a lot to acid-base chemistry. If you recall general chemistry or AP chemistry, there's a lot to it. So just so we don't lose our way, let's remind ourselves of our goal here. What is our overall goal or objective in reviewing this information? It is to be able to estimate the position of a Bronsted-Lowry acid-base equilibrium, a KAB, right? Semi-quantitative. From knowledge of what that acid-base equation is, which means from knowledge of the structures of the species involved in the acid-base reaction, right? Knowledge of the acid, knowledge of the base, and knowledge of the conjugates. That's our goal. And just a review from the previous lecture, we're going to pin everything in terms of that objective, right? Estimating KAB. We're going to pin everything on the pKa of the acid versus the conjugate acid. I should say though, and I've made one change to this slide, which you saw from the previous lecture, and that is in the upper right. KAB is favorable when the conjugate acid is weaker than the acid. We said that, but I added something else. KAB is also favorable when the conjugate base is weaker than the base. Okay, and that's because of the nature of conjugates, right? So this is just information, and we've identified the roles that the different species play, color-coded those, right? And keep in mind the inverse relationship between the value of the magnitude of pKa and the strength or weakness of an acid. And here's the review information on pKa with the critical statement, right? The more stable the conjugate base, the more favorable the reaction. And by reaction, what we mean when we refer to Ka or pKa, we are always referring to water being in the role of the base. Always, always, always. Okay? And so, again, the stronger the acid, the lower the pKa, and that follows from what you see here in these definitions. Okay, well, that's all well and good. But how practically are we going to know these pKa's? Are there tables of compounds and pKa's? Yes, there are. There are short tables. There are very long tables that go on for pages and pages because of the importance of acids and bases in chemistry in general. Chemists have for years measured or even calculated in some cases or extrapolated these pKa values for specific compounds. But we can't go running around with, a table that's 30 pages, 50 pages long. We need a better way of doing this. And again, we're not doing this in a strictly quantitative sense. We're doing this in a semi-quantitative sense. Now, the methodology of organic chemistry, as I think you're beginning to see, is can we learn skills so that we can evaluate a structure, and by a structure we mean, of course, a Lewis electron dot structure. And then can we make predictions on the properties or behavior or reactivity of that chemical species or compound based on that structure, based on that bonding, based on the functional groups. That's organic chemistry. And so can we do the same thing with the property pKa? And the answer is yes, we can. We can look for certain features in the structure that will raise or lower pKa's. And remember, it's always a relative raising or lowering, not an absolute one, because we're only comparing the pKa of the acid with the conjugate acid for a particular acid-base reaction. So yes, we can, and here's how we do it. There are, I list 7, maybe there are more. This is a pretty complete list. Let's say there are 7 structural factors that influence the acidity of an organic compound or of any chemical species, right? And remember, the more stable the conjugate base, which might be A minus or A, the more favorable the reaction, the stronger the acid, the lower the pKa. Let's look at these structural parameters and how they affect acidity. The first effect is the inductive effect, and these are not listed in any particular order. It's not like the first effect is the most important effect. The inductive effect, and I have an example here, and I do in every case, in every one of these parameters. So take a look, and these are pKa's that you're seeing here. Take a look at the pKa for acetic acid, which is in the upper left, is 4.74, around 4.7. Very, very, very well-known, well-studied pKa. Acetic acid is a very, very common and important, very simple organic acid, weak acid. Compare that to the compound right below it. So when we substitute the 3 hydrogens for 3 fluorine atoms, the pKa drops from 4.7 to 0.2. And remember, every unit change in pKa is a factor of 10 acidity, right? It's a logarithmic parameter, right? So that's a huge increase in acidity, right? Trifluoroacetic acid really can be considered to be a strong acid that completely dissociates in water, whereas acetic acid only partially dissociates. Go one more down, and you see the effect of distance on this inductive effect. And by inductive effect, we mean the effect of introducing electronegative atoms or functional groups that through the sigma bonding network or framework, right, induce a stabilization of the resulting negative charge in the conjugate base. Remember, it's all about stabilizing the conjugate base. That's what makes one acid stronger than another. You can see the distance effect is quite considerable. When we simply insert one CH2 and increase the distance by just 1 carbon, you can see that the effect is much less dramatic. So it falls off rapidly with distance, and this is of course consistent with Coulomb's law. Look at the compounds on the right. This is now, instead of fluorine, which is the most electronegative element in the periodic table, we use a nitro group, and nitro is very good at stabilizing negative charge. So one nitro group on the what is the alpha carbon of acetic acid, which you see in the upper right, changes the pKa from 4.7 to 1.7. But again, if we look at the effective distance, the effective distance is very significant, and if we extend that just by 1 carbon, the difference is now only 4.7 to 3.7. This is the inductive effect. For Bronsted-Lowry acids whose conjugate bases can be stabilized by resonance, we see a significant effect in the pKa. Look at this table, and I include this table on several of the slides in this presentation. It's just one of these tables of pKa's and specific compounds. So take a look at the pKa of butane, right, around 50, right, which is the weakest acid in this list. But compare butane at the top with methyl acetate in the middle, right, methyl acetate in the middle. You go from a pKa of 50 to 25, and this is largely due to the fact that the conjugate base of methyl acetate, and you can see which hydrogens are being removed there in red, and that conjugate base is resonance stabilized by that carbonyl group. If you then compare that ester at pKa 25 with acetone, which is the compound below it and pointed out in with the green arrow, you can see we've dropped another several pKa units, because instead of having the oxygen attached to the carbonyl, we have a methyl attached to the carbonyl, and the oxygen is more electron releasing, having lone pairs, which will destabilize the conjugate base. Finally, in the right-hand continuation of the table, you can see the additive effect of 2 carbonyls stabilizing the conjugate base. You can see that. And the pKa goes down to 13. And in fact, if those two carbonyls are, instead of ester carbonyls, if they're ketone carbonyls, the pKa goes down to 9 or 10. 9 or 10. That's extraordinary for a carbon-hydrogen bond. So the effect of resonance can be very significant. Here is the effect of hybridization. Compare again butane, pKa around 50, with propene, right below it, pKa around 43, and then below that with a terminal alkyne, pKa around 25, and R is just some alkyl group, right? The carbon hybridization is going from sp3 to sp2 to sp. The more S character, the more stable the conjugate base. And why is that? Because the more S character, right, electrons in s orbitals are held more closely to the nucleus than electrons in p orbitals. So the greater the s character in a hybrid orbital, the more closely the extra electron in the conjugate base is held to the nucleus, and the happier and more stable it is. The effect of hybridization on pKa. The effect of electronegativity. Again, compare butane, pKa 50, with ammonia, pKa 35, with water, pKa around 16. Okay, it's the difference between carbon bearing a negative charge versus nitrogen versus oxygen. The more electronegative the element, the more capable it is of stabilizing a negative charge. Pretty simple. What about the effect of charge? Okay, compare the pKa of hydroxide at 40 with water at 15.7 and H3O plus at negative 1.7. So you can see that if you're talking about an acid going to its conjugate base and the stabilization of that conjugate base, the last thing in the world you'd want would be an acid that already starts out with a negative charge, because it's going to take on a double negative charge as its conjugate base. So the more positive the charge, the more electron deficient the species is, the more acidic. You can see that in the oxygen series here. You can also see it for the nitrogen series, right? Amide anion NH2 minus, pKa greater than 50, drop down to ammonia, pKa 34, go down to ammonium, pKa 9, effective charge. Finally, we have the effect of size, and we only have 2 examples here in this table. Take a look at the pKa for methanol in the left-hand table at the bottom, around 17, very similar to water, not surprising. Compare that to the pKa of methyl mercaptan, which is the sulfur compound, sulfur analog of methanol in the right-hand panel, with a pKa of around 13. And so the larger sulfur atom, being a third row element, is better able to tolerate, right, the negative charge in its conjugate base, right? Charge density, greater charge density is associated in physics with less stability, or the converse of that would be if you spread charge out and delocalize it, and you can do that by resonance, or you can do that by looking at a larger atom, a larger volume to accommodate that extra electron. You can see that's a stabilizing feature as well. All right, so that's the introduction to these parameters. In the next video, we will apply them, and we'll do quite a few examples. And I think you can appreciate that some of these parameters might fight with one another. And that's in those cases, it can be difficult to come to a conclusion about the position of an acid-base equilibrium. When multiple parameters are in the same direction, it's very simple. When they fight with each other, it's hard to know which one to weight more than another. And so we'll take a look at that and a whole bunch of examples in the next video lesson. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.